Okay, hello. My name is Scott Grizzard. The little technical difficulties have been worked out. For some reason, it wanted the key again. I don't know why. And this is Discrete Math, the fall of 2020. And my air conditioning is not functioning like it should, so it's really, really hot in here. The AC guy was here. He 3 days ago, and ever since then the AC just has not been working right. It has not been. I think he probably some environmental group demanded that he replace the coolant that worked with something new, as they do. I don't know what it is. It's probably that the fan's not blowing or something, or he might have left a tool or something in the plug thing. Anyway, it's very warm up here. It's like 85 degrees in this room with the lights on. So anyway, that's enough me griping. How is everybody else doing today? So last time, and we'll get into the quiz, but we're playing around with the number theory, and our goal is to kind of get to modular arithmetic, but there are a couple of things we have to play with first. And so if my face is all shiny, that's why. So we need to get to modular arithmetic at some point, but we want to play with the things we need to play with first. So we need to set up the integers, and then we need to talk today. What we're going to be talking about is inverses for operations. So we're going to be talking about negative numbers and fractions in a way you probably haven't thought of them before. And when we do that, there's a reason why we're doing that is because we're setting up what's going to happen in different settings, because we got to get into modular arithmetic in order to talk about these security algorithms. So yeah, you're stressed. I'm stressed. I'm like way behind. I'm, trying to pass a qualifying exam. I'm way behind in my stuff because I'm teaching three classes. But hey, that's my job. So if you're working full time and trying to take my class, I'm working full time and trying to pass a big exam for my PhD. So I'm super stressed out too. But now we're talking about the fun math, right? We're going to be talking about making computers think, do math, and talking about math in terms of computers. So let's get into the quiz, and then we'll, I'm enough of me being human. Let me be the professor, and let's talk about this. It's not the end of my PhD, unfortunately. It's the end of the beginning. Passing this qualifying exam is the end of the beginning of my PhD. Okay, so let's talk about this quiz. And now the pins are back on there. I don't know what it is, but this thing likes to wander around. Okay, so what we wanted to do was we had a piece of code here. And what does this look like? We've seen this before, right? But instead, before I had the integers, right? Before I had the following. Before I had a equals and it was an array of 0, 1, 2, 3, 4, however you do that in PHP. I have to think about it. And then we had a for each a as whatever it was, x or whatever. Now we're doing the exact same thing, all right, but with a while loop. I know some of you who know programming already are going to be saying, well, why aren't you using a for loop? And the reason why is, again, my job is not to teach programming; it's to connect the programming to the way the computer works. The math to the way the computer works. So we're using while loops here instead because they're a lot more explicit about what's about to happen. So this while loop has I less than 5, and it's going to have j equals 0, and it's going to, of course, it's going to print a new line character. Who cares? But it's going to print foo and a tab character. So it's got two loops here. I've got two nested loops, just like I did before. So what's going to happen when I run this thing It's the exact same thing that happened before. So let's pull up the little software that runs it. Let's see. So let's see. I had it set up for the lecture, and I forgot that I needed to do the quiz. I needed to run this for the quiz. So this is the while loop.php. So when I run this thing, no student work is shown. When I run this thing, it looks like this, right? It's going to go foo, 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 foo. So every time, right, it's going to go J is 0, J, then it's going to go J1, J2, so 0, 1, 2, 3, 4, stop. Go up here, and now it's going to go I equals 1, 1, 2, 0, 1, 2, 3, 4, stop. I equals 2, etc., etc., etc. So what we wind up with is 25 runs of this thing. Okay, so how do we feel about that problem 1 to 5? Just the first part. All right. And if I want to see it, I can actually just put in here print foo let's see, print foo space, I want to dot I dot let's give it a little comma dot J, and then we'll give it the tab character again. That should do it. So if I want to see it actually run, I can do it like that, right? It's going to run foo, it's going to run foo 00, foo 01, foo 02, foo 03, foo 04, and it's going to do 10, etc., etc., etc. Okay, so it's going to loop just like these others did, just like it did before when I had the in. Right, and then it's gonna loop 5 times 5 times. By the you can do that, I think you mean that I just pull up the thing. I just ask it what's going on here, and that's what it gives me. Right, because it's got 2 nested loops. I'll save this as while loop solution. Okay. Well, it's not infinite because this thing increments, right? So it goes through 0 first, but then when it gets here, it increments the J. And then it increments the I right here. But it's not set to 0 back at the beginning. The J is set to 0, but only when I exit the loop, right? So every time you see this new line character here, right? Every time it's starting a new row, it's actually restarting this loop here. So the way this works is it's going to start with J equals 0. Right? I starts out at 0. Okay? Then it enters the loop. Yeah. So it works 1 loop at a time. It sets J to 0, prints a new line character, and then it starts this loop with J. And so this loop for J goes 0, print foo, increment. 1, print foo, increment. 2 print foo increment, 3 print foo increment, 4 print foo increment, 5, right? Increment to 5, and now 5 is not less than 5, so it goes, okay, let's go to the next I. So now I exit the loop, and I is no longer 0, I is now 1. I start back up here, I reset J, and I run J's loop again. And then I go out here, and I do that again and again and again. So the loops run one at a time in a nested fashion. And the plus plus is that increment. So if you look at the problem set, and you come up here, you'll see this increment operator here. And if you click on the page in here, it'll actually take you to that page. If you click here, it'll actually take you to that page in on PHP's thing. That's what that plus plus means. It actually means read and increment. So it reads first and then increments, as opposed to plus plus I, which would increment then read. But for the moment, yeah. That's the wrong one. Okay, well, this nested while loop does the same thing, except look at this one. This one here is like it only prints if I is less than J. Right? So just like before, I need to replace this with bar. Let's print it so it's all on the same line. So this is only going to print if I is less than J. I want while loop solution. Yeah. So someone has posted a decent facsimile of what the thing is happening as a loop in the chat, which is an excellent thing. But here I'm only going to print if 0, right? Here I'm going to do the same nested loop structure, but I'm only going to print sometimes. So I'm only going to print for 0, 1, 0, 2, 0, 3, 0, 4, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Right? Which is, of course, an enumeration of the set 4, choose 2. So I can write this in one of two ways. Right? I can write this as let me see. Where's the thing? So I can write this in one of two ways for the script of foo bar, print bar. It's either 0 plus 1 plus 2 plus 3 plus 4, which equals 10. Or I can think of it as 5 choose 2, which equals 10. So how do we feel about that one, 1 to 5? Okay. This beautiful drawing here. I love this drawing. I'll do it. I'm going to steal your drawing. J equals 0 is I greater than 5. Yes. Right. I plus plus. And it should be greater than or equal to 5. No. Then it's is J greater than or equal to 5. Yes. Escapes back to I do J plus plus, and I come back to here. Where do I go from here? I would go here. And I would do I++, not J++. And then the other way would be I print foo here, and then I do this should come back to here, right here. That drawing's actually more confusing. Yeah, so my drawing's not as good as the person who wrote it in chat. I should make a better drawing for that. But anyway, that's what it is. So that's that problem. Okay, question 2. And if you're confused about the while loops, you just have to read them very carefully and think about what the computer's doing. 5 choose 2. Well, the first one, 5 choose 3. Recall n choose k is equal to n choose n minus k. In other words, the thing's symmetric, right? The Pascal's triangle is symmetric. Right, so here n equals 5, k equals 2. So 5 choose 2 is equal to 5 choose 5 minus 2, which equals 5 choose 3. Check. All right, this equals 5 false 2 over 2 factorial. Remember, that's the formula. N false k times k factorial equals n false k. Check. Okay, well, this right here is the same thing. 5 false 2 over 2 factorial equals 5 times 4 over 2 times 1, which equals 20 over 2. Check. And 20 over 2 equals 10. I'm not going to explain the last one. How do we feel about that problem, 1 to 5? It's all of them. Okay. Right. So why is that so? Why is 5 choose 2 and 5 choose 3 the same? So if I have 5 cards, right, and I count the pairs, and I got comments that said, please, no more cards. Well, if you've got another finite set that you prefer, tell me. Now, if I count the ways I can give a pair, I've actually counted the triple too, right? If I count the pair 6 of spades, jack of diamonds, I've also counted the triple ace 4 8 of clubs, spades, and diamonds, respectively. Right? If I count this set, I've counted this set. Okay. The same thing holds if I do 52 choose 2. If I count the pairs in 52, I've also counted all the triples. I'm sorry, not all the triples. I've counted all the sets of 50 cards, right? So if I count the number of ways to deal 2 cards, that if I count this, I've also counted this pile of cards. Okay. That's simple, but really, really hard. Okay? That's a simple thing, but it's a hard argument, right? You hit yourself in the head when you get it, finally, but it's like, why couldn't I get this? Well, because it's hard. Simple, but hard. Right? Because what you're doing here, how are they equal to each other? Because what I'm doing is I'm counting the sets, right? I'm counting the number of pairs. Okay? if I count these two, if I count the set, if I count the way to these two cards dealt, it's the same as dealing these two cards. I could have dealt you 3 cards and kept 2, or dealt you 2 cards and kept 3. Okay? So when I count this, I also count this. It's not an easy thing. It's hard. It's simple, but it's hard. If you want to see a mathy if you want to see like an algebra reason, right? Think about what I'm doing here. If I take this formula, n falls k. Let's look at this. Let's look at n falls k over k factorial, and n falls n minus k over n minus k factorial. All right. Now, if you want an algebra reason, this right here is n times n minus 1 times n minus 2 times blah, 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 all the way down to n minus k plus 1. Over k times k minus 1 times k minus 2, etc., all the way down to 1. Now, compare that to this one here. This thing on top is n minus 1, ... all the way down to n minus k plus 1 over n minus k times n minus k minus 1 times n minus k minus 2 times ... all the way down to 1. So if I look at this example, that's actually more confusing. 5 choose 2 equals 5 times 4 over 2 times 1. And 5 times choose 3 is 5 times 4 times 3 over 3 times 2 times 1. The point is that a bunch of these things are going to cancel, and I'm going to wind up with the original. Because these things overlap, right? How do you feel about this idea that these terms are going to overlap each other? This is more confusing. So let's not do it in general. Let's just do it in the particular. If I do 5, choose... let's see. Let's not do 5. If I do 7, choose 3, that equals 7 times 6 times 5 over 3 times 2 times 1. Now, if I do 7, choose 4... that equals 7 times 6 times 5 times 4 over 4 times 2 times 1. And these 4's cancel. How about that? Oh. Sorry. 4 times 2 times 1. I'm sorry I didn't give you a lot of feedback. I was writing feedback for people that had major concerns, and you said you loved the class, and so I did that. Okay. So I'm sorry I didn't write you nice feedback, but I wrote feedback, and I didn't write it for everybody because I haven't gotten to everybody's, but I wrote a lot more detailed feedback for people that were having difficulty. Okay. That's enough about that. Yeah, I made a mistake there. I forgot the 3. All right, C equals AB, C union C. Union the set containing C. So this right here, I'm going to put the explanation down here. C union set containing C equals AB union C, which equals A, B, C. Yes, so someone asked me if that trick that I just used always works. Yes, it does. And I was trying to do it generally, but I'm just going to wind up confusing people, including myself, because the indices just get awful. So if you want to prove it in general, you can do it that way. You can write it out in general, but the indices get awful. So I just did it like this. And it's not right. If I do 7 falls 2, to come back to this one, if I do 7 falls 2, that's going to equal 7 times 6 over 2 times 1. And if I do 7 choose 5, 7 choose 2 is that, and 7 choose 5 is 7 times 6 times 5 times 4 times 3, 1, 2, 3, 4, 5, over 5 times 4 times 3 times 2 times 1, and this bit here and this bit here cancel. That's just too big of a cancel if you're still wrapped up in that. No, it's not. Yes. So in reality, it is 7 falls 4 over 4 falls 4 is the same thing as n falls k over k falls k. We just call k falls k, we call k factorial. So you are absolutely right. Are there any other questions? Okay. So you can think about it in terms of the formula, but you can also think about it in terms of the cards. The cards way is harder but simpler. The formula way, it's algebra, but it was, it's easier but more complicated. Okay. 1 to 5. How do we feel about question 3, by the way? Yeah, retakes. I'm behind. I'm posting the retakes. I forgot. So yes, I will put up the retakes for half credit. I just haven't put them up yet. Okay. So I spent half an hour on the quiz. Let's get to the meat. All right. So last time we talked about addition and multiplication. Oops, no, I don't want to. I want to move you over, Godel. I don't want to. Godel's not cooperating here. He's not moving over. There he goes. Okay. So last time we talked about let's see. Let's put some last time up here. So last time we did Godel. Last time we did this. So this was last time. As you can see, it's really hot up here, so I didn't spend the time up here making the thing look pretty. And why won't it like unindent? I don't know why it won't unindent. I'll figure that out later. We didn't do this. We did do that. We did define addition and we did do multiplication. Okay. So today what we want to do, we want to talk about properties of these things. And we want to define integers and rational numbers. And then we want to show, let's do exponents first. And then we want to show that if we define inverses for rational numbers, I'm sorry, we define inverses for exponents. We create irrational numbers. So this proof that we're going to do today is our first proof by contradiction. As if we get to it. So what we want to do is we want to kind of revisit what we did. So last time we had these two functions. We three functions. We had successor, addition, and multiplication. So now what we want to do is define some new ones. Okay. So we want to define a function that we're going to call powers. Okay, I'll call it powers. It's exponents. So let's just do that real fast. So exponents look like this. All right, so I'm going to do, and I'll call it powers, because pow is a reserved word in PHP. Powers takes as input, N and K. And this is going to define N to the K. So this is going to be powers. It's going to define N to the K. All right. Okay, so the powers thing, it's going to have N to the K. I'm going to let M equal 1. I'm going to let I equal 0. Same thing as we did for multiplication. But then what I'm going to do is while I is less than K, I'm going to define M as equal to the multiplication of Mn. So this is going to do multiply M by N. And I'm going to do this K times. So I've got a loop. I'm going to do I equals successor of K. I'm sorry, I equals the successor of I. And then I'm going to end my loop. And I'm going to return M. And I'm going to end the function. Okay. So I'm doing the exact same thing I did for multiplication pretty much. If you want to see what that will end up looking like, let me do it in such a way that I don't show the solution for the problem set. So if you want to see what that would end up looking like, it's going to end up looking something like this. Oops. Nope. There's no cat today. That's the wrong one. So when I do this, I called this exponential thing that I called powers. And I called it with, and then it's going to loop. And it's going to loop over multiplication, which is going to loop over addition, which is going to loop over the successor function. which is a complicated way of saying that I actually got the, this is to say that I'm using the old stuff. So I built addition on successor. We built multiplication on addition. And then we built exponents on multiplication. So how do we feel about that 1 to 5? This idea that once we built one of the procedures for doing something, we called that procedure in our next thing. Okay? So last time, what I did last time I used successor to build addition by simply applying the successor thing k times. N plus k was k calls to the successor function. Right? Then I did multiplication by calling the addition problem k times. And now I'm doing exponents by calling the multiplication multiplication k times. Okay. Okay. So again, the assignment was to create this off multiplication. Multiply the, oh, this just says what I'm doing. So I'm multiplying, I'm going to multiply m by n k times. And just make that my new m. Okay. Right, so in this example that I had, if I call in this example that I had, I called powers with n equals 3, k equals 2, right? And then I'm going to start I at 0, but then it's immediately going to call, multiplication for I equals 0. I'm sorry, multiplication for multiplication for n equals 1 and k equals 3, because it started with 1, m was 1, and then it called this, and then it called add here because it wanted to add one more here. So now I got this, and then it called it again, multiply again. Then it called add 3 times, and then it called multiplication again, and then it went back out. Okay. Now don't worry about the exact code. All right. The exact code is the exact code is not what's concerning. The thing that, well, worry about the exact code for the problem set, but not for this. Just remember that this thing's calling. And the point is that it looks like the multiplication and addition. But there's something weird that goes on here. So let's talk about properties of this. Okay? Let's talk about properties. And we're not going to prove them because proving requires recursion, which we're going to do in this class, but not yet. So properties here, add so for any L, M, and N, look at this. Add L, M equals add M, L. In other words, L plus M equals M plus L. This is called abelian or commutativity. You know you've made it. Oops, I'm looking at the wrong screen, aren't I? All right, this is called abelian or commutativity. And you know you've made it. Abel was a guy, and you know you've made it in math when they lowercase your name. Well, that's true for molt, too, right? But it's not true for exponents. Why? Exponents and molt look exactly the same, but why is this no longer true? That's weird. Doesn't hold for exponents. Okay. Well, what else is true? Add L, M, N equals add L, add M, N. What did I just say there? It says abelian or commutativity. If I say add L, M, N, add, these two things are true. What have I said? If I want to do it in our old operator notation, this is called functional notation. This is called operator notation, by the way. Operator notation is what you're used to. Functional notation is what it is. And by the way, in programming language, you can define your own operators for your objects. It's called overloading the thing. So you can define plus and define, and you do this all the time in Java. In Java, it basically begs it to happen, right? But you can define these things for your objects. All right, so what does this mean? Well, let's do a kind of translation here. What I said here, add of this. What I said was add. This said add L, M plus N, which is the same thing as saying L plus M plus N. Now, over here, I've said that this equals L plus add MN which means that what I've done is I've done L plus M plus N. So in operator notation, let me do all the operators in green. And it froze. Okay, well, it's not letting me change the operators to green. So what I've said here is L plus M plus N equals L plus M plus N. All right. This is called associativity. What am I saying? I'm saying there are certain properties of addition and multiplication that we want to know. In addition, mult of LM equals mult of mult these are associative as well. How do we feel about associativity 1 to 5? Yes, I'm saying for natural numbers. For any natural numbers. Right? So what I'm saying here, let me put an example. I'm saying 4 plus 3 equals 3 plus 4. I'm saying 4 times 3 equals 3 times 4. Okay? Here I'm saying 4 plus 3 plus 2 is the same thing as 4 plus 3 plus 2. And 4 times 3 times 2 is the exact same thing as 4 times 3 times 2. Now, how do we feel about it 1 to 5? I'm saying the order I do the operation doesn't matter, right? I can take 4 and add 3. I get 7 this week, and then add 2, I get 9. Or I could take 3 plus 2, which is 5 this week, and add 4, which gives me 9 again. Or I can do 12 and then double it, or I could quadruple 6. Well, it isn't all I had to say, because I could say this. Refresh your browser. I could say this here, but this is the more important thing. This is the thing that's harder. This is the thing that's deeper, right? The fact that, why should that be so? And more importantly, why shouldn't it be so with exponents? And I like these properties, by the way. I want to keep them. Yeah, but why not? That's the question. There's a deep question. Why shouldn't that work? If multiplication and exponents look just about the same when I code them, why shouldn't it be the case? It's kind of an interesting question. All right, and now I've got another one. Mult. Let me do this right. So I want to do multiplication. Okay, so add I want to molt first. Okay. Molt of L add Mn is the exact same thing as add of molt Lm, comma, molt Ln. Okay. So what I've just said there is that L times M plus N equals L times M plus L times N. This is called distributivity. Then give an example. 4 times 3 plus 2 is the same thing as 4 times 3 plus 4 times 2. How do we feel about that one, 1 to 5? Okay. And I want these to be true. Okay? These are true for the natural numbers. And I want them to be true if I expand things. Now, there are two special numbers here. I may not make contradiction today. Oh, well. There are two special numbers here. The first is 0. I. So that for any M in N, M plus I equals M. This is called the additive identity. Okay, and the answer is yes, it's 0, right? For all for any natural number, 0 plus n equals n. This is called the additive identity. And then for all n in the natural numbers, 1 times n equals n. So this is called the multiplicative identity. Okay. How do we feel about that? 1 to 5. Okay, a new name. All right. Now, wouldn't it be nice if for all n, for all n, we'll just say n, there was a number x so that n plus x equals 0. Wouldn't it be nice? So I'm going to add that in. So I'm going to define -1 equals is defined as the number x so that 1 plus x equals 0. I'm going to define -2 as the number x so that 2 plus x equals 0. One to 5, how do I feel like that? How do I feel about that? Yeah, that's right. So I'm going to add in, I'm going to union in some inverses. I'm going to create, I'm going to extend. So what I'm doing is I'm extending in this right here is the set of integers. And the set of integers is the set of the natural numbers along with all of the numbers I need to have an additive inverses. That means define. Define -1. The dot means basically it's like the equal operator in PHP. It means I'm creating this thing as this. So 1 to 5, how do we feel about that? I've just created a bunch of numbers. I think I may have already asked the 1 to 5 there. All right. This is the set Z. So this is called, if you wanted to find it on, it'd be math BB Z, the set of integers. So it's like the n. I have this thing. This is the kind of bold Z. It is a UTF-8 character. You can find it. It does exist. It has an HTML code. I don't know what it is off the top of my head. I think it has an HTML code. I know it has a UTF-8 code. All right. And I can do that for every numbers. I don't need to do that for 0, but I don't have to add a new number for 0, right? But it doesn't, it's not broken, right? -0 equals 0, and that's the only thing I haven't added. Right? A question that I might ask. I might give you Z and I might ask you to match it with something. Now, here's the kicker though. What happens if I want to do this for multiplication? Right? The integers are a warm-up. Don't worry too much about the integers. It's the rational numbers that are going to be where the meat is. What about multiplication? First, can I? I want x for all m. I want x so that x times n equals 1. For all n and z. Okay, so here's how I'm going to define 1/2. And this is key, because when we see this later, this idea, I don't want you to think of 1/2 as in half a pizza. Stop thinking of it that way. Okay? 1/2 is the number I multiply by 2 to get to 1. All right? Example. Create x so that x times 2 equals 1. All right? I want to create a multiplicative inverse for 2. Okay? So I am going to define something here. And again, get rid of 1/2 as half a pizza. That is no longer true in this class. 1/2 can equal 3 in some rings. It's in some of the things we're doing. So get rid of your concept of half as being a way to measure things. For this class, it's not that. For this class, 1/2 means the thing that I multiply by 2 to get back to 1. Okay? That's what 1/2 is for us. 2/4 as x so that x times 4 equals 2. Define 1/3 as the x so that x times 3 equals 1. How do we feel about this 1 to 5? What I'm doing here is I'm telling you to forget all of your stuff about multiplicative and forget fractions as you knew them. These are fractions for us. So forget fractions as you knew them. They're gone. Okay. They're gone because we're going to be talking about we're going to be talking about things. We're going to be talking about modulo arithmetic. And in modular arithmetic, 1/2 might actually be there, or 1/2 may be completely undefined and I might not be able to do it. Okay, so now I need to extend, okay? I need to extend in. I need to extend addition and multiplication. On our new sets. Okay? So how do I extend addition? Right? So for negative numbers, define add negative n k as equal to -1 times n k. So to extend, and then define add I'm sorry, that's wrong. I'm thinking multiplication in my head already. Don't do that. I got to define multiplication first and then do addition. Define mult negative nk as equal to negative mult nk. Define, let me see here. What was the other thing I needed to define first before I could do addition? I remember you had to do multiplication before you did addition. Define -1 times n is equal to -n. There was something else I needed to do, and I don't remember what it was. I'll remember it later, and then I'll post it. It's taking too long anyway. I also need to define, for fractions, I'm going to define P over Q equals I over J if Pj equals Qi. And I'm going to define P over Q plus I over J as equaling to Pj plus Qi all over Qj. All right, I do remember how to do that. I'm going to have to look at my notes because I got to look up this, and I want to get to one last thing before we close today. So I'll pick that up next time. You have to bootstrap these, and I don't remember how to do it, which order they have to go in. I know what they are, but I don't remember which order it is to get them to bootstrap, so I got to look it up. I thought I remembered that off the top of my head. Anyway, skip ahead. Can I define 1 over 0? So can I define bootstrap? Okay, so bootstrapping in a computer, does everyone know what booting a computer means? The computer kind of builds itself up. So bootstrapping is this idea, and you see when you see like the Java bootstrapper or whatever like that, you know, the different bootstrappers. The idea is that what you're doing is you build one thing, then you use that to pick up the next thing, then you use that to pick up the next thing, and so on and so on. Like lifting, like if you're climbing and you're pulling yourself up by your bootstraps. So that's called bootstrapping type thing. That's the idea anyway. So you have to do these in order. So you have to do one and then the other and then the other and then the other and then the other. And I don't remember the order off the top of my head. And I should, because I'm teaching this class and I should be like, oh, I remember everything. I come in, I come in this morning, right? I didn't look this stuff up. I just remember it off the top of my head. Well, the question is, can I? Why not? Why is 1 over 0 undefined? Why must it be? Can I? Why not? I've just defined 1/2. 1/2 wasn't defined before. 1/3 wasn't defined before. I just created it. Well, why not? Why can't I just create a number for 1 over 0? Why can't I just create one? I mean, I could. Why not? I actually can. If you want to think of this, I don't have all the properties, but I actually can, in some math systems, define 1 over 0. I can't if I want all the properties. Okay? I can't if I want to preserve the properties. I can if I don't care about preserving all the properties. So I can do that. Watch me. I'll define this real fast. Watch this. So what I'm going to do is I'm going to take the real line and I'm going to add infinity to each end. Okay? Here's 0. Now, I take these things, I take this real line, and I'm going to glue it together. So I am going to say, okay, now let negative infinity equal infinity. This should not be in red. This should be in like light thing. So instead of a line now, I have a giant circle. Here's infinity. These are the negative numbers. These are the positive numbers. And x over 0 for any x except 0, x over 0 equals infinity. Okay? I've just said, let's take the entire real number line, glue it together. We're going to create this thing called infinity, and we're just going to have it be that. Now, I lose certain things, right? Because now 1 plus infinity, now I've lost order, right? I lose properties of the real number line if I do this. But I want to preserve these properties. I want to preserve these properties. I want add, multiply, add. I want commutativity, associativity, and distributivity. Okay? But I want those properties. So suppose I could. Suppose I could do that. Suppose I could have 1 over 0 and 2 over 0. All right. If that's the case, I'm defining 1 over 0 as the x so that 0 times x equals 1. And 2 over 0 equals y so that 0 times y equals 2. 1 to 5, how do we feel about that? Again, forget everything you know about fractions. All right, well, if that's true, 0 times x equals 1. 0 times y equals 2. That means 0 times x plus 0 times x equals 2 equals 0 times y. I didn't say that y plus anything had to be 0. Note that for any natural number, 0 times n equals 0, but I haven't said anything about fractions. Right? That doesn't mean that there can't be a fraction that times 0 equals something else. Well, if I distribute this, right, I have that means here that 0 times the quantity x plus x equals 0 times y. So that means that 0 times 2 x equals 0 times y. But 0 times 2 equals 0. This right here equals 0 because that's true for every natural number. So I've got 0 times x equals 0 times y. In other words, I've got 1 equaling 2. Oh, and that's bad, by the way. How do we feel about that? 1 to 5. I know I'm 5 minutes over now. If I do that, that means that 1 over 0 and 2 over 0 can't exist. And that's exactly what it is, a proof by contradiction. And we'll pick that up next time. And we'll do the most famous one of all. Okay. But I can do it for all the others. Let me just define what Q is here. So Q equals P over Q, so that P is an integer, Q is a positive integer. And this is the set of fractions. And that's what we'll pick up next time. So next time I'll finish exponents. So next time, okay, so next time I'll do that. So the important things from today, the big summary for today, I messed up the fraction thing because I couldn't remember how to bootstrap it. But the big thing is to remember that I'm defining multiplicative inverses here. Okay, so this is the big thing from today, is that I'm defining 1/3 as the x, so that x times 3 equals 2. Okay, and these types of things. So now I'm creating these new sets. Okay, and I'm calling that set Q. All right. It seems to me like this was not my biggest hit lecture, and I'm sorry for that. But you didn't have as much fun. But some of these, we actually have to do it before we can get into the really fun stuff. We actually kind of do have to kind of bootstrap this stuff, annoyingly. And I will see you guys on Tuesday. Scroll down. You mean like that or the other way? This is a Q. So proof by contradiction is where I take two things and I assert that they're both true and then show that if so, then I wind up with a contradiction in my logic, which is bad. Contradictions are bad. Yes, 1 equals 4 is bad because 1 does not equal 4. Well, you've actually already come up to the contradiction. You've actually already found the contradiction already when you say 1 equals 4, because 1 does not equal 4. But the why is important. Why can't you define 0 over 1 and... I'm sorry, why can't you define 1 over 0 and 2 over 0? And the reason you can't is because you wind up with a contradiction. You wind up with 1 equaling 2. If you want these properties. Now, if you don't care about those properties, you can toss them. You can have them. The point is that it's the properties. Any other questions? Oh, I've got people that are unhappy with me. I'm sorry you're unhappy. But it is the nature of the thing. All right, I'm going to sign off here. If you have any questions, go ahead and send them to me. I'm going to get out of this hot room, though. I'm going to go downstairs because the AC is not working. And I will see you guys later.